Welcome to Lecture 3.1, Determinant Prerequisites. In this section, we will study the determinant of a linear map without a choice of basis. In other words, the determinant of a map, not a matrix. It turns out that this is an n-linear function, which you can think of as a generalization of a bilinear function. So we will study k-linear functions in a later lecture. But to do that, we need to study permutations first. We need a little bit of prerequisites, hence the name. And before we even do that, I will give you motivation for what a determinant really is. Otherwise, we're working toward this idea that maybe you saw in undergraduate linear algebra, it's a number attached to a matrix, but what does it really mean? So that's how we'll start, with an intuitive definition of the determinant. And using the intuitive definition, I will prove I will convince you of some of the properties that you know and love, so you know what we're going to work for. And then we will finish this lecture with permutations. Okay, let's get started. Here is our unofficial definition of the determinant. Now, determinants in general are only defined for linear maps from a vector space to itself. And this unofficial definition really only makes sense for Rn to itself, so not Cn or not Z2n. So this is the signed volume of the image of the unit n cubed. So that's how we write the n cubed. And let me give you a few pictures as to what I mean by that. So first of all, in R1, the unit n cubed is just the interval 0, 1. It's a pretty boring case. In R2, the unit n cubed is, so if you look at E1 and E2, that determines a square. And so a linear map T is going to send this square to some other parallelogram, and the determinant is just the area of that. So this is TE1 and this is TE2. And then in R3, the unit n cubed, the unit 3 cubed, is just is the standard unit cube. And if we apply t, now I don't know if I'm going to be able to draw this, these three vectors determine a parallel pipehead. I think I'm going to fail in this one, but I think you get the basic idea. Something like this. And the volume of that is the determinant. Now, several things. First of all, I said sign volume. I mean n-dimensional volume. So that's length here, area here, and three-dimensional volume here. Okay, so let me give you a more detailed picture of this. So I'll do this R2 case larger. Now this is similar to a picture that I did in a previous lecture, you may remember. And I really strongly recommend thinking about think about linear maps this way. So start with, so here we are, this is R2, and when we pick a basis, we have determined a coordinate system. And you can think of that as a grid. So this point here is 3 of these and 1 of these. And every basis determines a different coordinate system. So what T does, I like to give you multiple ways to think about this. One of them is ignore the coordinate system. Just draw dots. Make this a red dot. Make this a green dot. Make this a yellow dot. Make this a blue dot. And where do those dots get sent to other dots over here? And that's kind of a basis-free way to think about this. Now, a non-basis-free way to think of it is take a basis here, and E1 will get sent somewhere. So E1 might get sent here. Let's say TE1, and maybe E2 gets sent here. So this is TE2. So now this determines a new grid of parallelograms. This is a new coordinate system. So now these colorful dots, where do they get mapped? This red one gets mapped here, 1, 1 to 1, 1. This green one gets mapped here. Again, 2E1 plus E2, 2 of these and 1 of the. Oh, actually, sorry, I flipped the order of this. So 2E1 is here, and E2 is there. So actually, the green dot should be here. The yellow dot should be here, because again, the yellow dot is 1 of these, 2 of these, so we got to go 1 of these, 2 of these, and then the blue dot is here. Okay, so here the determinant of this is up to sign the area of this. So the area here is the determinant of t. And I say absolute value because I haven't told you if it's positive or negative. Now notice that in here we have a reflection. See, these things swapped orientation. So here we have E1 and E2, and here we have them in opposite order. In other words, these 4 dots, this green yellow is now over here was yellow green. So if we had like a little smiley face here, something like this with the tongue out, then over here it would get mapped to, I really don't know how to draw this well, something like that, a mirror reflection of it. So because of this mirror reflection, the determinant of this is negative. So in this case, this thing over here has area 1, and this thing here has, I don't know, what is that area, like 2.5 or 3? Let's say 2.5. So the determinant of this linear map is negative 2.5. Okay, so that's how you should think about the determinant. I mean, it really is, it's the scaling factor. You know, how much does a piece of area over here get stretched or scaled by over here? And you can imagine how this works in 3-dimensional space or 1-dimensional space or n-dimensional space. So here are some properties of the determinant, purely based on this geometric definition. So first of all, one of the most important ones is determinant of t is 0 if and only if t is not invertible. Now, what do I mean by that? So this linear map, you can always just undo it. You know, how do you undo this? You send this thing, the inverse is going to send this guy back to here, and it's going to send this guy back to here. So actually, I didn't finish my sentence. You can't always undo this, but you can always undo this ... if there's some positive area here. So if this area is positive, or is positive, if it's non-zero, then or negative if you count it as sign, then that means that these sides, the images of these vectors, do not lie in the same line. So anytime you have that, you can undo this, and conversely, anytime that you, so let me draw this picture up here. So suppose instead you map E1 and E2 gets mapped to the same thing like this, then the entire line, now you have collapsed this entire 2-dimensional grid onto a single line. There's no way you can pull that apart. Now, wherever this gets mapped to in an attempt of an inverse, this thing gets mapped to a scalar as well. So that's a neat property of this, and you can imagine in 3-dimensional space, if this unit cube gets mapped onto a plane, so it gets mapped to some parallelogram, then you can't undo that. So that's the first thing. The next thing is that the determinant of TS equals the determinant of T times the determinant of S. Now the way to think about this, I wish I'd give myself a little more room for this, but I think this is easy enough to do here. I can make it small, and I don't think I'll lose very much. So suppose T maps R2 to R2, so say in this manner, and so here are the parallelograms. So the area, so you have a stretching factor, which is the determinant of T. And let me see. Actually, as I've drawn it here, I should be going. How about if I do this? How about if I do ST? It doesn't really matter, and these are both numbers, so the order here doesn't matter. So to be consistent with this, let me say determinant of ST. Now, if I do the determinant of or if I do S, now this is going to map it to some other, I don't know, maybe I'm trying to figure out how to draw this thing. Maybe it maps it to, I'm trying to draw a grid, some grid here, and I'm probably failing at this, but so here your stretching factor is determinant of T, and here your stretching factor is determinant of S. So the composition of these maps from here is ST. So do T, then S. So the stretching factor of this composition is clearly just a stretch. So if this stretches it by 2 and this stretches it by 1.5, then you just multiply 2 times 1.5 to get the total stretching. And I think that should be intuitive. So if you blow this up by 2, you blow this up by 3, it doesn't reflect my picture, then this whole thing is blown up by 6. And the reflections take this into account as well. Okay, so that's the second one. And finally, the last one that I want to say is that the determinant of T is linear in each column. Now, what do I mean by this is or row. And so, i.e., if T is obtained from S by multiplying a column or row by C, then the determinant of T is just C times the determinant of S. Now look at this picture here. If I had taken T and I had, so multiplying a column, so let's do column first, and row is really similar. So if you multiply a column by T, so like say the first column, well first of all I should say that the first, with respect to this basis, the first column of T is the image of the first basis vector. So if I multiply that column by 2, what I've done is this vector gets stretched by a factor of 2. So now my parallelogram, the image of the unit square, is now double. Similarly, if I multiply the second column by 3, now I've tripled the length. And if in general, if I multiply one side length of a parallelogram or parallelepiped by C, then I multiply the volume by C. That's just intuitive. That's what we know about volumes. Now there's one more definition, or one more property that I want to do. I almost forgot about it, so I will do it up here. And this is almost immediate from what I basically told you unofficially what signed volume is. And this is swapping two rows or columns flips the sign of the determinant of T. Now, I guess in this unofficial definition, it should be clear why columns hold, because columns of a matrix correspond to the actual side lengths of this parallelepiped. Rows, it's not quite so clear. Now, you may remember that the determinant of a matrix and its transpose are the same, and that will indeed be the case. But anyways, overall, this is what I want you to think about determinants as we move forward. So as we build up these multilinear forms, starting in the next lecture, this is why we are doing it. This is what we are trying to move toward and formalize. We will now spend the rest of the lecture reviewing permutations. We all know what a permutation is, even if we don't know any math. The idea of permuting a collection of chairs or people makes sense. And if you've taken abstract algebra, then you have probably studied this a lot, but I'm not going to assume that. So throughout, this bracket n is going to be the set of numbers 1 up to n, and a permutation is a bijection from that set to itself. There are n factorial permutations of n objects, and these comprise what are called the symmetric group, denoted Sn. Now, you don't need to know that this is a group. We are not going to use the fact that it's a group. I'm just giving this to you because this is what it's called. It's a nice name for it. And I will use Sn to denote the set of permutations. We won't use the group structure. You certainly don't need the definition of a discriminant to define a permutation, but this actually makes it quite convenient. So the discriminant of n variables, x1 up to xn, is the following. So it is the product of the difference of all pairs xi minus xj, where I is less than j. Okay, so I'll do an example of this shortly, but why are we defining this? Well, in short, because it's a quick and dirty way to define the sign sign of a permutation. Namely, if we permute the variables, then the discriminant is only going to change up to sign, either plus or minus 1. So if it doesn't change, we call that an even permutation. If it changes, we call it an odd permutation. Now, you may have heard about these even and odd permutations before. There's other ways to define it, which we'll see some of these in the next slide, like whether or not they can be generated with an even or odd number of transpositions. But if we try to define it like that, it's not even clear that that definition is well defined. You know, maybe you need, in one case, an even number, and in another case, an odd number of transpositions. And I'm going to define transpositions on the next slide as well. I'm getting a little bit ahead of myself. But for now, let's go back and do an example of this so we can really understand what this is all about, because otherwise it's just this messy looking equation. So let's do it when n equals 4. So the discriminant of, say, x1, x2, x3, and x4. Now there are 6 pairs of distinct numbers between 1 and 4, so that's going to be x1 minus x2, x1 minus x3, x1 minus x4, x2 minus x3, x2 minus x4, x3 minus x4. Okay, so let's now permute these variables. Let's do it several different ways. One of them is if the first one we'll do is if we just swap the first 2 entries. So let's call this 1, 2, 3, 4. This is probably the easiest way to denote this permutation. If you have seen cycle notation, then that is written as 1, 2. So 1 goes to 2, 2 goes to 1. You can write it as in a table. So 1, 2, 3, 4. 1 goes to 2, 2 goes to 1, 3 is fixed, and 4 is fixed. This is I, and this is pi of I. So anyways, if we do this, then we end up swapping just the first 2 entries, x2, x1, x3, and x4. So here, one way to think about this is we are swapping x1 and x2. So these things swap, and we get x2 minus x1, which is the negative of this. And then what else swaps? So this x, let's do this in red. This x1 and this x2 are going to swap. So notice these come in pairs, x1 minus x3 and x2 minus x3. Swapping x1 and x2 has a net effect of nothing. Similarly, this x1 minus x4 and x2 minus x4, if we swap these, so swapping x1 and x2 is going to swap those 2 terms, but the net effect is nothing. And then we have terms like this that don't involve a 1 or a 2. Swapping x1 and x2 does nothing. So this thing here is just going to, this new one is how about if I just do this? So the net effect is nothing. Well, I guess the last 5 terms, but this first term is the negative of this. So we get the negative of the discriminant. So this permutation is, hold on a second. I haven't defined it yet, but we'll define it soon. This is what we will call an odd permutation. Now it's a little more complicated if we use some more things. So if we swap 1 and 4, it's going to be x4, x2, x3, x1. Now this is going to change a lot more things. So now, if you look at this, the only two things that are actually in the same relative order are 2 and 3. 2 is less than 3. Everything else is going to swap. So now 2 comes before relative to the first one. So 4 comes before 1. 2 is before 1. 4 is before 2. 3 is before 1. So what you have with the original 5, you have all of these things swap sign except 2 and 3. So what we get is we get a, so this is the same. Here we get a negative 1 times, here we get a negative 1 times this, negative. So we get 5 terms that flip sign, 1 that does not. And so this is going to be, again, a negative p of x1, x2, x3, x4. Okay, so let's do one more. Let's do a p. Let's how about a x? So let's cyclically shift these. So one goes like this. So p x3, x1, x2. So if we oh, I forgot my x4. Sorry about that. So here we have x x3 minus x1. I don't know if it's really worth doing this, but whatever. I'll do it quick. x3 minus x2, x3 minus x4. Now x1 minus x2, x1 minus x4, and x2 minus x4. So let's see how many of these have swapped sign relative to here. So anyone swap sign is when they're in the reverse order. So here that's in the reverse order, that's in the reverse order, and that's it. So the other 4 are in 3 is less than 4, 1's less than 2, 1's less than 4, 2's less than 4. So this is going to be equal to positive 1 times the discriminant. So this is what we will call an even, I put 2 commas in there, x2, x3, x4. This is what we will call an even permutation, though I will define that in the next slide. So this is nice because this is a really easy, well-defined way to define the sign of a permutation without having to talk about the number of transpositions, because that is not necessarily unique. So I've talked about transpositions because I know a lot of you know what this is, but a transposition is a permutation that swaps 2 entries and fixes the rest. In other words, for some I and j, tau sends I to j, j to I, and everything else is fixed. And one way to write this in cycle notation is just ij. So I goes to j goes to I, and everything else is fixed. And I don't think I need to review cycle notation because I don't think we're going to use it much. If we do, I will bring it back, but it's one of those things that I encourage you to look up, but it's really not something that we're going to study much. Okay, so I will finish this lecture with a straightforward proposition that has 5 parts that will all be left as a homework exercise about some basic properties of the sign of permutations. Now remember, the sign, sometimes it's called the signature of a permutation, by the way, is either +1 or -1, depending on whether or not permuting the variables flips the sign of the determinant or not. So first of all, sign is multiplicative. So the sign of the composition of 2 permutations is just the product of the signs. That should make sense if because you can do this product in 2 steps. You either flip by plus or minus 1 twice, and if you do it twice, then -1 times -1 is 1. Otherwise, -1 times 1 in either order is going to be -1. And if neither of these permutations flip the discriminant, then their composition won't either. Next, the sign of any transposition is always -1. Now that was pretty clear if we had an adjacent transposition like 1, 2 in our previous slide. It was less clear when we had 1, 4 because we had 5 things that got flipped. And it's going to be even less clear if we have like n equals 50 and we're swapping like 2 and 18. But there is a simple argument for why this is equal to -1, and I'll let you think about this. It's a good exercise. Next, every permutation can be written as a composition of transpositions. This should be fairly intuitive for why this is true. So suppose you have 5 chairs and you have people sitting in these chairs, A, B, C, D, and E. And then 1, 2 is the transposition that swaps the people in the first 2 seats. 2, 3 swaps the people in the next 2. 3, 4, and 4, 5 are defined similarly. Then it should be clear that I can achieve any seating arrangement or any permutation of these people by successively applying some sort of, some sequence of transpositions. So for example, if I want D to be up in the first chair, I can apply 3, 4, then 2, 3, then 1, 2 to filter D up here. And then I can put whoever I want in the next chair and so forth. But it's still worth writing this up formally in a nice, coherent, and concise argument. Next, well, it's clear that the number k is not unique because I can always take, for any decomposition, I can always stick on a tau, 2 copies of a tau 1, and these things obviously are just the identity. They undo each other, and now I have a longer string of transpositions that equal pi. However, the parity of this decomposition is unique. In other words, if I can write pi with 10 transpositions, I cannot ever use 101, no matter how I try, because that's an odd number. Finally, the culmination of this is that if you have a permutation pi, that's a composition of k transpositions, then its sign is -1 to the k. So think about how this follows from all of these. So we know that sign is multiplicative. So the sign is just the product of the signs of these transpositions. And we know that each transposition is -1. And we know that the parity of this decomposition is unique. Okay, so that brings us to the end of this lecture. We will start in the next lecture with k-linear forms and then go from there. Hope you stick with us.